Alright guys, welcome back to the channel. This is Dave Lucas with Injection Molding Skills and More. Almost got tongue tied. Okay, Dave Lucas with Injection Skills and More. Today's video we're going to go over hot manifold systems. What they do, how they work in the field, the advantages of them, and the disadvantages of them, okay? So I'm going to go over the 7 advantages that you have with them and try to read out some stuff that I wrote down. And then I'm going to show you guys some small videos of one that's got like an angled view. And then I'm going to show you some of them that I have on my desk as far as the drops, the heaters, how the TC cables are actually woven into it and everything. So I'm going to go over this with you. So the 7 advantages of a hot runner system is eliminating the runner. So if you think about it, with material costs, you know, being so expensive, and cold runner systems, whether your company lets you run rig grind or not, and most medical or food, they cannot run the rig grind at all. So that's actually eliminating the runner, helps with cost and everything. Okay, the next one would be cycle time reduction and lower processing. So on this one, in most cases, the runner actually weighs more than the part does sometimes, guys. So half of the total weight is actually the thicker sections of the molded part. Wall thickness, it says the cold runner, if you reduce the cycle time and cooling time, controls the thicker sections. So on this, like if you take the runner completely out of it, you can run faster cycle times, lower cost because you're not molding the runner now. Okay, so then the next one would be improved molding system efficiency. So on this one, let's say you have the hot runner molds are generally easier to start because of there aren't any solidified runners or removing after each shot. So on this, like say you got a part and you're running it, you got to take the runner out every single time. So this means you can run it a lot faster. Automatic cycles can begin faster, and then plus you can actually get going a lot better on it. Okay, so the next one would be optimal part quality. So on this one, you actually when the plastic flows through the cold runner system, there's less heat that you're using actually on this part. Okay, causing pressure drops that can result in sink marks and unfilled parts. A hot runner system, on the other hand, maintains a balanced melt flow and a consistent temperature from the machine nozzles all the way through the gate and fully into the pack and hold of each cavity. Okay, so that's why it's optimal part. So if you look at this picture here, you can see these are the heaters, these are the drops, and then you got your tips down here at the bottom. So what they're saying is you fill in right here, it fills completely all the way out, stays maintained heat all the way through this whole thing. So then the next one would be molding automation. Okay, so on this one, you could drive cost and everything on this by flash-free plastic parts. Hot runner mold advantages are when with automation, because in addition to part dimensional consistency, you're able to automatically keep running and running and running and running and not have no issues with it. Okay, so that with the automation, it really helps you. Then if you don't have no runner in there, you're just grabbing the parts, putting the parts on the conveyor belt or dropping them somewhere else. Design flexibility is number 6. And on this one it says a major hot runner advantage is which very little is written is the ability to locate the gates at a wide variety of different points on a part. So let's say you have a part that's really big, you can actually put your valve gates anywhere you want because you can make the design of this however you want it to be. Okay, so that's your design flexibility. Okay, and then the last one would be balanced melt flow. So on this one, you got the flow advantage that a hot runner have is that the melt channels are in separate heated manifolds. So separate, so like I said, right here you got this whole channel here. This is a manifold, this is a manifold, this is a manifold. So, and then these are drops that come off of the manifold. Then you got a sprue bushing heater here. So what they're saying is the thing on the balance, you're getting the same distance. So when it fills in from here, whatever if you short shot it, if the same distance here as it would be here on this valve gate system. Okay. Let me show you guys something. So this here would be a picture of, like, okay, so you have your nozzle tip down here. You got your nozzle body, which they call this a drop in most cases. You have the valve pin, which this is the needle that runs inside there that actually lifts up and down inside the manifold system. Then you have the seal ring, you have the heater, the manifold block that runs across, the cylinder unit that comes down. Okay, then you have the nozzle thermocouple, which is on the outside. So I'm going to show you one that I have sitting here. Your heater tube, which actually it wraps around this more or less, so it heats everything up. So this is kind of like a breakdown of kind of how it looks. I know it ain't very good, but hey, I was trying. So, but let me show you guys. Let me turn the camera around here. I want to show you guys what the heaters look like. So, all right. So if you have a couple heaters, this is an older one. So what you have is this is a heater that goes onto the manifold. You drop this down in there. This is the thermocouple that runs on the side of it. And then you can see the heater, it's built right into this. And then down here at the bottom is where your tip would be. So your valve gate pin would go down in through here and come out down through here. The tip of it would. So this is an older one that's been used. Here's a new one. You can actually see the heater that's embedded into it. So if you're looking at it, you can see all the heater is already woven into it. And then you put your tip on the very end of this. Your needle goes down through here that actually runs the valve gates, and then you have your cylinder on top of that. So this is like just a heater that you can replace. So I'm going to show you guys a couple videos inside this video, and then I'll get back with you guys. All right, peace. I wanted to show you guys, this is an angled manifold system. So these are all angled in an angle going in there. I just wanted to show you this brief little video of this. They came out with these like about, say probably about, I don't know, 8 or 9 years ago for better sealing and fit. So you got your cylinders on the top that are at an angle. So you have your hydraulic cylinders. Right there's the heaters. So you got the back heater, the front heater. You got your hydraulic cylinder. Tip. This is the drop. Valve gate pin. I just wanted to add this to the video just to show you guys. So there's a collar that pulls out. You can disassemble the head to replace the pin if you ever had to replace the pin. This is the plunger system that sits inside the hydraulic cylinder on top that actually moves the pin up and down. So you take that off. Right there's the pin. The pin cap goes on top of that. So what they did is they put a cooling ring. So this is a cooling ring that goes around there to help cool it. There's all kinds of different designs, guys. So you'd have Saventive, you have Husky, you have Moldmaster, DME, Gamma Flux. I mean, there's tons of different hot runner systems out there. This one's an angled one. I just wanted to show you how it's angled and everything. Most of them are just straight forward. So this is through Husky.
The hot runner nozzle, also called the hot drop, is the connection between the manifold and the mold cavity. The position of the nozzle and how it seals to the manifold is critical to the hot runner molding process. If a nozzle is not positioned correctly, it can result in nozzle and gate damage, along with material leakage. Nozzle sealing is accomplished by spring force, thermal expansion, or by directly bolting the nozzle to the manifold. Virtually all nozzles have some alignment feature, usually a high tolerance surface in the gate detail that is used to ensure that the nozzle tip is aligned properly with the gate. During heating and cooling, the top of the rigidly attached nozzle moves as the manifold contracts and expands. There must be a robust seal between the nozzle housing and the manifold.
In an effort to mold parts more accurately and efficiently, many companies today design their molds with a hot runner or hot manifold system. It has even been projected that 60% of all new molds built in the USA next year will be equipped with hot manifold systems. They have several advantages over cold runner systems, including scrap reduction, minimal gate vestige, improved cycle time, better process control, more part design options, no need for runner removal, robotics, or separators. On the downside, the hot manifold systems can experience a catastrophic failure known as encapsulation, or the flooding of a manifold where a leak fills the entire system with plastic. Wires, thermocouples, heaters, nozzles, and sometimes even the control box can be encapsulated in hardened plastic, which is extremely difficult to remove. There are two choices for cleaning up the system. The first choice is to send it to a qualified service center where the system will be placed in an oven at high temperatures to burn off the excess plastic. The advantage of this method is a fast turnaround with new thermocouples and heaters. The disadvantage is cost. New thermocouples and heaters are expensive. For a 48-cavity mold, the thermocouples cost $120 and the heaters are at $320. Sending this mold out for repair would cost the company $24,000 just in thermocouples and heaters, not including other needed parts and labor, which could make the total $30,000. Time is also a factor. It may take about a week to have the mold returned, or longer if 48 heaters cannot be quickly found. The second choice is to clean it in-house. This option can save thousands of dollars, including a 50% to 75% savings just in thermocouples and heaters. A determination also can be made from where the leak came. Knowledge can be gained on how to prevent future leaks and the overall operation of the system. In-house repairs properly executed will always save time and money. There are disadvantages to an in-house repair. It can take 40 man-hours or more to completely clean and rewire the system on a typical 48-cavity mold, even longer if you don't have the proper equipment. Cleaning and repairing an encapsulated system also requires a higher skill level to troubleshoot, clean, and reassemble without further damage. Failing to do this correctly can cause the system to flood again due to a totally unrelated issue that caused the first flooding. Many hot runner manifold problems can be traced back to a lack of knowledge concerning hot runner, assembly mistakes, poor work habits, improper tools used during the clean and repair of the manifold, and critical components. Here are some methods and tools that will make it possible to separate the wires properly and safely. Allowing the heaters and thermocouples to be removed. This must be done first in order to remove the nozzles from the plate for cleaning and inspection. Our mold is a 48-cavity valve gate system that was completely flooded from the front or nozzle tip side of the hot half of the mold. It appears that there was a major leak between the nozzle seal and the cavity block, allowing the plastic to flow into the wire channels, then back into the manifold. Unfortunately, this completely encased the wires in plastic, or in this case, polypropylene. Several different colors could be seen, so the leak was not detected immediately. Since the mold is going to need a complete teardown, the electric control box, manifolds, and bridge have been removed. All wires have been numbered and disconnected so they can be thread through the wire channels in the plate one at a time. On this mold, the thermocouple wires run along the entire length of the nozzle, making removal from the front impossible. This will necessitate removing the nozzle from the back just to get to the thermocouple. On better designed systems, thermocouples are easily removed from the front of the mold instead of requiring a complete manifold removal just to change out a defective one. Make sure the necessary safety equipment is present. This includes a full face mask, heat-resistant gloves, and a shop coat. A vacuum system to draw off as much of the smoke as possible is desirable, as is plenty of light. Tilting the mold back at about a 20-degree angle is helpful to get it into a more comfortable working position, resulting in better control of melting and separating the wires. The objective is to see exactly where the wires are routed through the channel, and to which heater, so the wrong wire will not be pulled, which could break it. Even though the control box has been disconnected and removed, the heaters can still be warmed up to remove the plastic that surrounds them. Using a special tool and a direct connection to a 110-volt plug, the individual band heaters can be heated to remove the plastic that surrounds them, giving us a better view of the wiring around each nozzle. Our ohm meter has a temperature probe built into it, allowing for the monitoring of the temperature as the heater warms up. Once these are removed, the next step is to trace and free up all of the wires. The typical method for freeing the wires is to utilize a heat gun that puts out about 1200 degrees of air, but in a wide area. This gun is useful since it won't burn up the wiring easily, as its heat is not concentrated. It melts the plastic slowly. Many times the wiring is tangled up, which makes it difficult to trace what wire is going where, unless you can push the plastic away with a small tool. Another tool, which is quickly becoming a favorite here at tooling docks, is used whenever there is a need to melt and remove plastic. That tool is the laser blade. This tool expels hot air, around 800 to 1000 degrees, but at a much higher velocity than a typical heat gun. The high velocity air helps to move the melted plastic off the wires to better expose which wire is the focus and to trace and free it faster. Patience and careful attention to the location of the heat gun must be used as the heater and thermocouple wires are easily burned or damaged during removal. It takes a bit of practice to correctly gauge the distance from the hot tip of the gun to the wires, and then judge the speed at which to move the gun. Once the wires have been freed, they can be fed through the wire channels. The heaters are warmed up again to expand them, which aids greatly in their removal from the nozzle. Sometimes there can be a problem such as a stripped bolt head. A square-headed easy-out makes quick work of this problem. When the nozzle is ready, use a hammer and special punch that is soft and configured correctly to tap the nozzle out of the plate. In our case, the thermocouple will be removed with the nozzle. Set the assembly aside and continue until all nozzles are removed from the plate and the components are ready for cleaning. To learn more about hot runner...
Okay guys, I hope you guys enjoyed those videos. It showed you a little bit about how they work, all the different drops and all the nozzle tips that pulled out, and then what happens if you get one that leaks by. What they do is on some manifold systems, what they'll do is they'll take like at these points here and they'll put shim in there to actually force this down to where these seat off better down inside the pocket area. So that happens a lot. Like I said earlier in the video, there's all kinds of different companies that make manifold systems. So you got Saventive, Hot Runner, Gamma Flux, DME. These are all different kinds of companies. Husky. I mean, there's so many. I'm probably forgetting half of them, but they make designs for you to help you out to where you go runnerless. It helps you out on a lot of different variables. So, like I said, there's your sprue bushing. Material flows into there, flows down the length of the part on each of these, and fills down through each one of these to fill the part out correctly. So, I hope you guys enjoyed the video. I hope I was informative. I hope I give you the knowledge that you need. If you have any questions, anything at all, please like, share, and subscribe. Till next time, peace.